Okay, bom dia. My name is Lisa Glendenning, and today I'm going to talk about how we achieve scalability, scalable consistency in scatter, which is a distributed key value storage system. Oh, I'm sorry, remote malfunction. Okay. Okay, so many prominent internet services today rely on key value stores, broadly defined. These systems have a wide range of use cases and environments, ranging from a small number of well-provisioned machines to a global network of end users. So let's take a look at VOOS. VOOS is a peer-to-peer network with millions of users, and it uses a class of key value store called a distributed hash table, or DHT. DHTs can be classed as highly scalable but weakly consistent. At another extreme, we have classic database management systems such as MySQL, and these systems are strongly consistent but not very scalable. We'll see that many of these systems deliberately trade off consistency and scalability, but is this really necessary? So in Scatter, we set out to answer the following question. How would you build a distributed key value storage system with both scalability and consistency? So now I'm going to overview our goals for Scatter. First, Scatter provides strict consistency. Scatter implements linearizable consistency semantics for key value operations. Also, Scatter scales to hundreds of nodes in a wide area network. Also, we designed Scatter for high availability, but Scatter does not choose availability over consistency. And finally, later in the talk, I'm going to show you that scalable consistency is practical. We'll show you results showing that scalable consistency does not have a large performance cost. To achieve these goals, we combine ideas from a lot of existing systems. In particular, we combine techniques from both scalable peer-to-peer systems and from consistent data center systems. So for Scatter, we borrow the basic model of a distributed hash table, but we organize nodes into fault-tolerant groups. Nodes within a group use consensus protocols to replicate state and to manage it consistently. We also need to coordinate operations across multiple groups, and for this we use distributed transactions with groups coordinate in a localized fashion to update state across multiple groups consistently. So Scatter starts with the basic model of a distributed hash table. Distributed hash tables are a class of key value store that are highly scalable but weakly consistent. So here we have a basic DHT model. The keys are represented by the circle on the inside. This is a set of all keys called the key space. The set of all nodes in the system is arranged on the outside of the circle to represent the assignment of keys to nodes. So each node in the DHT has just partial knowledge of the system structure. In this case, each node knows the key range that it is assigned to, and it knows its predecessor node and its successor node. These predecessor and successor links form an overlay in the system, and this overlay is used to traverse the DHT to find the mapping of keys to nodes. In this case, we're showing a ring topology, and that is what we use in Scatter. DHTs are designed for a highly dynamic environment, which is why we model our system after them. Nodes join and leave at any time, and this is called churn. So to manage churn, DHTs implement ad hoc protocols where the nodes that are locally affected by a change coordinate directly with each other. And this is the problem. This is where inconsistencies come from in DHTs. So to make this more concrete, I'm going to go over an example and show you what can go wrong and where these inconsistencies come from. In this example, a node C wants to join a DHT, and it decides to pick a point between the nodes A and B in the DHT. So in order for C to join the system, we need to update state across all three of these nodes, A, B, and C. So what needs to happen is that C first needs to locate its predecessor node A and its successor node B and tell them that it's taking over some of the keys between them. Now, ideally, we would like the system to transition from the beginning state, where C is not a part of the system, to the final state where A, B, and C have all been updated correctly. The problem is that this join operation is not atomic. So what happens is that there's a sequence of steps that needs to happen on all three of these nodes, and these steps are just executed in a straightforward fashion. Also, the intermediate state produced by a partial execution of this operation is observable externally. So what could go wrong here? Well, here I'm going to give you 3 examples of what could happen, but there's actually a lot more things that could go wrong. So one example is that there could be some sort of communication fault between B and C, and this will lead to the case where C correctly takes over some of the keys that are already owned by B, but B is not aware of this, so then we have the case where multiple nodes own the same set of keys. Another problem that could happen is that C could fail right after it's taken over some keys from B. So in this case, we have a gap in the DHT where there's a set of keys that are not owned by any node. And this will persist for some time until this is corrected by the DHT. And finally, there could be a communication fault between A and C. What would happen in this case is that A would never update its successor pointer from B to C, and routes that go through A would skip over C and go to B. So basically, the problem is that this operation is happening simultaneously with a lot of arbitrary failures, and that this operation is not atomic. So I gave you a few specific examples of what could go wrong with that join operation, but really we could come up with a much longer list. The problem is that DHTs use these ad hoc protocols to add and remove nodes. So we need to ask all these questions, like what happens with concurrent operations? For example, what happens if 2 nodes join at the same place and at the same time? A similar scenario would be what happens when 2 adjacent nodes fail at the same time, because all of these detection algorithms for failures are local. Another common problem is that one node thinks that a node next to it has failed, when in reality that node is just fine. So failure detection is a challenge, and this can be made worse by non-transitive communication faults. So you could probably come up with a complete list of all of these different corner cases and try to program your DHT protocol around them, but really this approach is error-prone. So we decided to do something different. So what did we do to adjust these problems? Well, first, Scatter borrows the DHT basic system model, but we organized nodes into fault-tolerant groups. Within groups, the nodes use state machine replication techniques, and this masks a lot of the complexities and failures that are seen when dealing with individual nodes. The last thing we do is we design techniques for groups to coordinate with each other. Now that we have these groups that are fault-tolerant components, we could use them in protocols such as distributed transactions. So now I'm going to talk a little bit more about the actual scatter group in some more detail. So first, all state within a group is replicated using Paxos. This state includes the configuration of the group, such as the member nodes of the group, the keys that are assigned to the group, and who the leader is. Also, all key value pairs are replicated across all nodes of the group. Since we're using Paxos replicated state machines, changes to group membership, such as individual node joins and individual node failures, are managed using reconfiguration algorithms. So what this means is that really the data is only at risk if a majority of the group fails before it's able to reconfigure. So, like other systems that use consensus protocols, scatter elects the leader. Now, the problem with this is that we don't want all operations to go through the leader and force the leader to become a bottleneck. So, the next technique we use within a group is we partition all of the group's keys among all of the nodes of the group. So each node also uses Paxos to order client operations on keys, and all of the operations are replicated across all the other nodes of the group. So what in effect this means is that client requests can be parallelized across the group instead of being serialized through the leader alone. And again, this gives us increased performance. I'm not going to show you the graph, but it's in the paper. So we're already doing pretty good by having this fault-tolerant group. It already addresses node joins and node failures in a consistent way, and data replication. But there's limitations to what you can do with a single group. So you can ask the obvious questions. Well, what happens if a group just loses a lot of nodes? It's going to become too small and it's going to fail. The other side of the coin is that large groups are safer, but they're also going to be slower in performance because of the consensus protocols that we use. Another issue that we like to address is that we would like scatter to balance workload across multiple groups rather than just having all client operations going through a single group and having the other groups be underutilized. So, to solve these problems, we implemented what we call MultiGroup Operations. These operations include merging two small groups into one, and the inverse operation of splitting one large group into two. And we also have multi-group operations to rebalance keys and nodes between groups. We implemented multi-group operations by using distributed transactions across groups, and these transactions are only involving the groups that are locally affected by a change, and they're coordinated locally. So you might ask, well, how would you actually implement distributed transaction across groups of nodes? Because classically, a distributed transaction is executed across individual nodes. So here I'm going to go through an example to make this more concrete. You might say, well, since each group already elects a leader, then we can just execute the two-phase commit algorithm between the leaders of groups. So here we have group B. It wants to split into two groups, B1 and B2. Only two other groups are involved in the transaction, that is groups A and group C, because their predecessor and successor pointers are basically being modified by this transaction. So first, we will have the leader of B send a prepare message to the leaders of groups A and group C. When the leaders of groups A and C receive this message, and they're not involved in any conflicting transactions, then they'll respond with a vote to commit. When B receives all of these responses, the leader of B will decide to commit the transaction and go ahead and let everyone know, okay, we're going to go ahead and do this split. Transaction's committed. Then B will use what's called a reconfiguration algorithm to split the one group B into the two groups B1 and B2, and at the same time, A and C are going to update their predecessor and successor pointers. So you can immediately see that there's going to be a number of problems with this approach. We can ask the same kind of questions about this idea that we did earlier with DHTs. In particular, what happens if the leader B fails? You get into all sorts of bad situations. So what we're going to do is we're going to use the power of the group abstraction that we already have in scatter. So what this means is that basically the leader of the group is going to replicate every step of the two-phase commit protocol before actually executing that step. You can think of this as equivalent to using a write-ahead log. Instead of flushing to disk, we are replicating the log entry. So what scatter actually does is what I'm going to go through now. So first, the leader of B replicates the decision to split. Then it sends a message to A and C. When A and C receive this message, they also replicate that this transaction is starting, and they replicate their vote. Then they reply with the message to B. When B receives this message, it decides to commit the transaction. It replicates this outcome of the transaction. Once this has been replicated, then the transaction has actually been committed. Once it's committed, B can send the outcome to both A and C and reconfigure into the two groups B1 and B2. At this point, A and B will also replicate the outcome, and they will update their predecessor and successor pointers. To recap, Scatter provides linearizable consistency semantics, and we do this using consensus protocols within a group and distribute transactions across a group. We have shown how Scatter is designed for scalability in wide area network by dealing with faults and by having all operations be localized. We have also shown that Scatter is designed for high availability because we replicate all data and we reconfigure when new resources become available. And finally, I've talked about how Scatter is designed to have high performance. We do this through a number of techniques, including the partitioning of keys within a group and a number of optimizations that I'm not going to talk about here, but you can find in our paper. For the remainder of the talk, I'm going to overview a couple of main results from our paper. We're really interested in answering two questions. So the first question is, how robust is Scatter in a high churn peer-to-peer environment? The second question that we set out to answer is, okay, so say you're given a more ideal environment, a low churn data center environment, then in that case, how does Scatter adapt to dynamic workload and how well does Scatter scale? We compared Scatter against two different systems, OpenDHT in the peer-to-peer case and Zookeeper in the data center case. We did this to have a baseline of comparison for the metrics that we collected. So first, I'm going to talk about our comparison against OpenDHT. OpenDHT is an open source DHT that has been deployed on Planet Lab for a few years. In order to do a fair comparison, we re-implemented OpenDHT's routing algorithm, and we layered it on top of Scatter's groups. Routes in OpenDHT are log n, and we use them basically as cached hints. Most of the time they work. If for some reason the cached hints are out of date, we can always fall back on the consistent ring topology maintained by Scatter. We use application-level benchmarks by implementing an application called Chirp that's Twitter-like. And for our workload, we use traces from a Twitter measurement study. We deployed both systems in Planet Lab with 840 nodes, and we varied the rate of churn that we injected. So here we have two graphs showing the measured consistency and availability of both Scatter and OpenDHT. The x-axis is churn, and it decreases from left to right. The y-axis on the consistency graph is the percentage of read operations that were consistent, and the y-axis on the availability graph is the percentage of read operations that completed within a certain time period. So as you can see, we designed Scatter for consistency, and we found 0 inconsistencies. We also found that Scatter is more available than OpenDHT, and we believe that this is because of our design for the consistent ring topology. So now the question that's probably on your mind is, okay, consistency is great, but how much is it going to cost me? And the answer is, we don't think it's going to cost you very much. So here we show the latency of read operations in both Scatter and OpenDHT. Again, the x-axis is churn, and the y-axis is the latency of read operations. So you can see that OpenDHT performs slightly better here than Scatter, but the difference is not very much. It's about 10 to 12% in these results. The final graph I'm going to show you is from our comparison with Zookeeper. So Zookeeper is an open source coordination service that was developed by Yahoo, and it's in use in production systems. Now, since Zookeeper is only designed to scale to a small number of nodes, about 5, In order to do a large-scale experiment, we had to actually build a new system out of multiple zookeepers. So we call this system replicated zookeeper. And the way that we built this is we statically partition the key space to multiple instantiations of zookeeper. Our experimental setup is a little bit different because we're interested in a more data center setup. So we use MULab, and we varied the total number of nodes in the system. We did not inject any churn in this experiment, and we used the same chirp workload from the OpenDHT experiments. And we also used this workload to set up our partitioning of replicated zookeeper. We divide the workload into two halves. We use the first half for partitioning, and we use the second half to actually run the experiment. So in this graph, the x-axis is the total number of nodes in the system, and the y-axis is the throughput of thousands of write operations per second. So ideally, what we like to see is linear scalability with the number of nodes in the system, and Scatter achieves this. Zookeeper scales sublinearly. And we also plot the standard deviation on this graph, and you can see that Zookeeper has higher variance. So the takeaway point from this graph is that dynamic partitioning adapts to changes in workload better than static partitioning with no coordination across multiple instances. In summary, Scatter uses consensus groups of nodes as fault-tolerant building blocks. Scatter also implements distributed transactions across groups to repartition the global key space and to modify state across groups. Finally, evaluation against OpenDHT and Zookeeper shows strict consistency, linear scalability, and high availability. Thank you.
The question is, what is new?
Okay, the question is, what did we do new in our system? To the best of our knowledge, we are the only strongly consistent system that is scalable to a large number of nodes across a wide area network.
Hi, Mike Friedman from Princeton. I guess the question is, there's obviously issues with strong consistency, liveness assumptions about if you have various partitions in your system or failures. So I guess the question is, you were targeting a relatively small number. I mean, Planet Lab is something we're all limited by, I guess. But the target setting was something like VUs. Do you know if you've done any measurement studies or characteristics of uptime or node behavior in VUs, whether or not you would actually be able to provide these guarantees under the churn that you actually see in these systems?
So the churn that we use in our experiments is actually based on measurement studies of peer-to-peer systems. We use a Pareto distribution, and the lowest churn rate that we evaluate 100, which is a mean lifetime of 100 seconds, is actually pretty aggressive. It's possible that we could test our system under even smaller churn rates. Again, I'm not sure.
I guess the question is not if you want to say you achieve strong consistency, it is not what is the churn for the average group, but actually if you look at the tail of the distribution, are there groups for which you actually have too many faults, and therefore in some sense you can't achieve linearizability, and therefore the question is, what do you say? You obviously need to give up liveness.
Oh, I see. So what you're asking is, well, what if you have group failure? Is that what you're asking? So in that case, we still always achieve linearizable consistency, but yes, we will lose liveness in that case.
So you achieve safety but lose liveness?
Yes.
Okay, thank you.
Hakeem Weatherspoon, Cornell University. I was wondering what happens if you lost more than F members in a group. Were the other groups able to then take over that part of the ring space?
So again, I think this question is about what happens if a group fails. Again, we've designed Scatter so that this is a very, very low probability. Of course, no system can avoid every single failure scenario out there. In this case, there would just be unavailability in the key space. But again, addressing the situation is future work. We can envision a system where groups could take over the key spaces of adjacent groups that have failed.
Okay. I Hussam Mablubde from Cornell University. A couple of slides back, you showed the cost of providing strong consistency by comparing it to OpenDHT, and I think in the paper you mentioned that your implementation of scatter uses a whole lot of policies to do load balancing and minimize latency and such. And I was wondering, if we include such policies in a system like OpenDHT, would the difference in cost increase or still be comparable?
Okay, so what you're asking is, well, for scatter, you have a lot of policies and other optimizations that you didn't really talk about here. Is it possible that if we included those in OpenDHT, that OpenDHT would perform much better? I would answer that OpenDHT has actually been through a lot of iterations. They've actually done another number of optimizations already. It is possible that both of us could optimize our systems further and shift this graph some way or another. It's a little hard to say.
Marcos Aguilera from Microsoft Research, Silicon Valley. I was wondering whether in your design you think of a group, the processes or the machines in a group being close to each other, or do you allow the machines to be in geographically distant locations?
So the question that you're asking is, what about correlated failures? So if you're optimizing groups such that all the nodes are close to each other geographically so you get lower latency, then yes, you can risk some correlated failures and have a higher failure or higher probability of group failure. So the answer, this goes back to policies, which I didn't actually talk about in this talk, but we have in our paper. We actually have a number of policies that we implemented in scatter. One would say, well, I value latency over having a group fail. So in that case, the system would be optimized for larger group sizes. But we also have a separate policy saying, I really value robustness. And in that case, scatter groups would adjust themselves so that they are over a wider geographical area. Of course, in that case, you see lower latency. I mean, higher latency.
Okay, last question. Sid Sen, Princeton University. So I have a question which you may not have the answer to, but I noticed that if you're dealing with faults that are a little worse, like more malicious, you probably can't do some of the optimizations you do, like have each, divide the key space among primaries. But my bigger question was, if you had within each group, if you were running a more heavyweight protocol, like something that required all-to-all communication, do you have any idea how that would affect the performance in your peer-to-peer setting?
Well, my intuition is that, performance would get worse. I don't have a more concrete intuition than that. Again, we have optimized the system a lot to get the performance that you see. And I suspect a lot of these optimizations would still be possible, or there's some other things you could do with a different set of protocols. Perhaps ones that address Byzantine faults and other faults that we don't have in our current system.
All right, thank you.